Hi. Today we want to talk about sequences of numbers. So let's start in. We described a set as a collection in which order doesn't matter and repeats collapse. And what does that mean, order doesn't matter and repeats collapse? So, for example, if I take the collection 3 and 2 and 5 and 4 are all in the collection, that's the same collection as the one that contains a 2, a 3, a 4, and a 5. Likewise, if I take a collection that contains 3 and also 3 and also 4 and also 4, that's the same collection as the one that takes 3 and 4. The repeats collapse there. A multiset is a collection where order doesn't matter, repeats do not collapse. And an example where repeats do not collapse is, suppose you want to draw a bar chart of the heights of people in the room. So you go around the room, you measure people's heights, and some people have the same height as other people, 67, 67, 67. You don't want those to go away. So you want to keep repeats. On the other hand, the order doesn't matter. There's no particular order to this data set. I just happen to go left to right in the room. So order doesn't matter, but repeats do not collapse. Okay, so that's called a multiset, sometimes called a bag in artificial intelligence, although I think the term multiset is getting to be pretty universal at this point. So then what's a sequence? What's a topic for the day? And so a sequence is a collection where order does matter and repeats do not collapse. Order does matter and repeats do not collapse. That is to say, a sequence is an ordered list. We use diamond brackets to denote a sequence. The notation is not universal, but again, I think it's becoming more and more common. So I'll have a sequence, I'll call the sequence capital S here, that consists of S0, S1, all the way up to Sn, and you see the diamond brackets to hold it, in contrast to the curly braces for a set. Here's an infinite sequence, T0, T1, all the way up. Elements in a sequence are called terms. It's just a vocabulary word, it doesn't matter. And the place that a term has in a sequence is its index. So this, you would call that, you would say that's sort of S1 is, you might say that term 1, you might say this is term 0. You might say this is term N. Sometimes, somewhat confusingly, even though that says S0, we will start by calling it the first term. That's just like the same reason we call the year, we say the year 54 AD, we say that's in the first century. It's just one of those things. So just as an example, the sequence of multiples of 7 is 0, 7, 14, 21, etc. We may write S0 equals 0, S1 equals 7, and as an example, the term 14 as index 2. Okay. So just vocabulary words, that's all. Just going to list some common sequences to talk about ones that we'll see as we move through the semester, and also ones that occur all the time. So arithmetic progression is a sequence of numbers that have the same difference. So my example down here, arithmetic progression, 4, 7, 10, 13, a person spots right away that there's always 3 between the numbers. So you would say the initial term is 4 and the common difference is 3. Geometric progression is one where instead of always adding the same thing every time, instead you multiply by the same thing every time. So here, 2/3, 2/9, 2/27. Every time we're multiplying by 1 over 3. So you would say here that the common ratio, or the common factor, is 1/3. Initial term is 2/3. I'm going to list some sequences that a person runs across, that a person knows, just to try to make the point here that this is a familiar topic, in case you haven't noticed it's a familiar topic. So there's a sequence of primes, infinite sequence. So it makes perfectly good sense for a sequence to be infinite. Sometimes that's what you want. The sequence of perfect squares. The sequence of triangular numbers. I tried to pick one that was maybe a little less familiar, but still one that a person might have run across. What's with the bowling balls? Well, let's see. So you call these triangular numbers because if you make up a triangle of dots, a triangle with dots that has only one row has just one dot. A triangle of dots that has 2 rows has 1 dot, 2, 3, so that's a total of 3 dots. A triangle of dots that has 3 rows has 1, 2, 3, 4, 5, 6. So that's why they're called triangular numbers, because if you make up a triangle with evenly spaced dots in it, that's how many you get. Well, when you go to a bowling alley, that's how many. There's 4 rows in the triangle, so there's a total of 10 pins. Okay, and then 15, and etc. The Fibonacci numbers, familiar Fibonacci numbers. And just to do an example of one that's unfamiliar, the so-called self-describing sequence contains f of k occurrences of k for each k. So start counting at 1. So it has a 1 in this sequence. It has one occurrence of 1. It has 2 occurrences of 2. So I'm using f of k to denote the value of the kth term. So the value of the first term is 1, the value of the second term is 2. It has 2 2's in it. So it's got to have 2, see the 2 there? It's got to have 2 3's in it. And then how many 4's is it's going to have 3 4's in it. And it's going to have 3 5's in it. It's going to have 4 6's like that. That's why it's called the self-describing sequences. Okay, so just an example of a sequence that has a name, important enough to have it. It has a name, but probably you never saw it before. The hailstone sequence. So you start with the number n, and you make a sequence by the rule. For each term in the sequence, if t is even, then the next term is t over 2. If t is odd, then the next term is 3t plus 1. So let's start, how about number 5? So 5 is odd. 3 times 5 plus 1 makes 16. 16 is even. Half of 16 is 8. 8 is even. Half of 8 is 4. 4 is even. Half of 4 is 2. 2 is even. Half of 2 is 1. So just to do another example here, how about the 3? 3 is odd, so 3 times 3 plus 1 is 10. 10 is even, half of 10 is 5. 5 is odd, 3 times 5 plus 1 is 16, and we've been there before. 16, then 8, then 4, then 2, then 1. This is called the hailstone sequence because it goes up and down seemingly at random. I'm not sure you can call it random because there's a rule for it, but it seems to bounce up and down like hailstones in a cloud. You'll notice that every one, I've only listed a couple here, but every one of these hailstone sequences associated with some initial number ends in 1. So, for example, here's the hailstone sequence for 7, and it too ends at 1, although it takes a long time to get there. It nonetheless ends at 1. The Collatz conjecture is that each hailstone sequence eventually reaches 1, and nobody knows if it's true. Sequences, very interesting topic. The online encyclopedia of integer sequences is the place. If you go to the slide, you'll see that that's a link. OEIS.org. Online Encyclopedia of Integer Sequences. A go to check for sequence. So if you have some sequence that you're working with and you think, I wonder if anything is known about that sequence, you go there and it gives you all the information known about that sequence. Sometimes very handy. Okay, well, we did sequences for a couple of reasons, but one of the reasons we did sequences is because we're going to want to look at the case where you add the numbers up in a sequence. You take all the numbers in sequence and add them together. That's called summation, obviously. So we often want to add up the elements in a sequence. So for example, if you write down the odd numbers, 1, 3, 5, 7, etc., just the familiar odd numbers, and you add them up. So 1, there's 1, 3. There's 1 plus 3. 5, 1 plus 3 plus 5. 7, 1 plus 3 plus 5 plus 7. When you add up the odd numbers, you get, whoops, there's a mistake there. Sorry about that. That's supposed to be 25. I typed in 55, just a typo. I apologize. And then 36. So the sum of a sequence of numbers, AM through AN, is given in this notation. You can write it as AM through AN added up, or you can write it using a capital Greek letter sigma. It says I equals M to N, A sub I. So I equals M to N, A sub I. So that Greek letter sigma, you can remember that sigma is S type of letter, and it stands for summation. In the notation, when it says I equals M to N, in the notation, both A sub M and A sub N are included. Okay. So for example, if I gave you A0, A1, A2, A3, 3, 4, 5, and 6, and I asked you for the sum, I equals 1 to 3 of a sub I, I'm asking for a sub 1 plus a sub 2 plus a sub 3. And you add them up, they happen to add to 15. The point is that I'm asking for a sum of this subsequence of the given sequence. Okay, so just notation, not especially hard notation, and probably notation you've seen before, but nonetheless notation. Another example, if you take the powers of 2, and I want to sum up the indices I equals 0 to n. I'm adding up 1 plus 2 plus 3, 1 plus 2 plus 4 plus 8 plus 16, etc. So if I add just the 1, there I am, 1 plus 2, 1 plus 2 plus 4, 1 plus 2 plus 4 plus 8, 1 plus 2 plus 4 plus 8 plus 16, 1 plus 2 plus 4 plus 8 plus 16 plus 32. And a person notices, of course, about this sequence that it is the power of 2 minus 1. So this is 2 to the 1 minus 1, this is 2 to the 2 minus 1, 2 to the 3 minus 1, 2 to the 4 minus 1, 2 to the 5 minus 1, like that. I'm introducing summation of sequences because we're going to develop a way to prove formulas like the one that I just cited, namely that the sum of the powers of 2 is the next power of 2, take away 1. Here's a famous example, one that comes up all the time. It seems like hardly a week goes by when I don't find myself summing a geometric sequence. So if you add up all the numbers in a geometric sequence, where to get from one number to the other, you multiply by r, multiply by r, multiply by r, multiply by r, etc. You add those all up. The formula there is that you factor out the a, and you're looking at r to the n plus 1, take away 1, over r, take away 1. And a person should memorize that formula. Very important formula. A person should memorize it. That example, the formula takes in n. Here's the n right here. The formula takes in n and gives us the formula for the sum of those numbers. So we often want such a formula. We often want a formula to give us the total for summation instead of having to add the numbers up all at once. We can just drop it into the formula and have the answer. And again, we're going to develop a tool that enables us to prove such formulas. So here's another example. Suppose you want to add, instead of adding numbers in a geometric sequence, I'm going to add numbers in an arithmetic sequence. So I just took the numbers 0, 1, 2, all the way up to 100 and added them up. So I'm adding the numbers 1 plus 2, etc., all the way up to 100. Let's have a look on a piece of paper. I'm adding the numbers 1 plus 2 plus 3 plus 4 plus all the way up plus 99 plus 100. Okay, and there's a way to do this that a person may have seen some variation on this, but I'm gonna do the variation I like the best, and that is I'm gonna add it twice. I'm gonna write it down here, and then I'm going to write them in reverse order. 100 plus 99 plus 98 plus all the way out to plus 2 plus 1. So I wrote it twice. You add them up. The reason for writing it twice is because 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101, and so there's a pattern. So there's a pattern. When there's a pattern, there's usually a way to figure out what's happening. This is a total of 100 times 101. But of course, I added it twice, so I don't want the original number. So the answer is, I don't want the twice. I want to divide 1 plus 2 plus 3 plus all the way up to plus 100 is 100 times 101 over 2. And in general, one plus 2 plus 3 plus all the way up to plus n is n times n plus 1 all over 2. Very important formula. Ooh, I should put parentheses. Very important formula. Good. Let me get back to my screen here. There we go. Okay. So for example, you add up the numbers 1 to 100, it turns out to be 50-50. And there's the general formula. I have a comment about the notation. The notation is very ugly. So when you look at the sum I equals m to n of ai, then you're including both am and an. You're including both am and an. And that's unfortunate. That's too bad. Because what you want is, pop this down again. There we go. What you want is, you want that if you add a sequence, I equals, say, 7 to 15 AI, plus I equals 15 to 27 AI, you should get I equals 7 to 27. That's what you hope. That would be the right thing, the capital R right thing. But the answer, of course, I wouldn't be asking the question if it wasn't true. The answer is no. The answer is what you get over here is you get A7 plus all the way up to plus A15. And then here you get A15 plus all the way up to plus A27. And so you've got A15 twice. That's not right. That's not right. So, in fact, what you want instead is you want to say something like this. You want to say something like this. You want to say I between 7 and 15, less than or equal to on the left, greater than or equal to on the right, AI. That's the right way to do it. Now, that's not by any means the most popular way or any such thing, but this is a good habit to cultivate. Less than or equal to on the left, less than on the right. I'll note, while I'm on the topic here, I'll note that this is how Python does it. One of the nice things about Python is it does the right thing here. That if you say range 1 to 5, it gives you A1, A2, A3, A4. That's what you want. You want less than or equal to on the left. You want less than on the right. Commas in between. Okay? Okay, so a small point about notation, but one that I have personally been tripped up by many hundreds of times. So you want to be careful about that. Whoops. And you can read about that in this. I have a topic at the back here that I'm not going to go over, but you can read about that if you click on that link. I did want to make a comment here about the formula that's on the top of this piece of paper, n times n plus 1 over 2. Everybody is familiar with the fact that managing software projects is very difficult, and the first person who said it compellingly is this person, Frederick Brooks, who managed the first really large software project trying to develop an operating system for IBM computers. He wrote the classic book, Mythical Man Month, that we have in the library and that everybody who is interested in computers should absolutely read, if not memorize. One observation that he made is that if you have a programming project that's running late and you assign extra programmers to it, you can make it run even later. When a project has I many programmers and you add a new one, that adds I many coordination requirements. The new programmer has to coordinate with all the old programmers. Okay, that's right. You got to make sure that the interface for your functions is all the same. That all makes sense. Of course it does. Of course it does. So the total number of meetings needed for an n plus 1 programmer, an n programmer team is n times n plus 1 over 2. N squared, that is to say the number of meetings needed rises with the square of the number of programmers. The number of coordinations necessary rises with the square of the number of programmers. So when you're pouring programmers into a program, into a job, the amount of coordination necessary explodes, rises with the square of the number of programmers, and can grow to overwhelm the programmers. So this particular formula is interesting because it illustrates that although programmers grows linearly, coordination requirements grows quadratically. Okay. Okay, very good. All right, so we'll see you next time.